We've been talking about water all through this course. Water in the atmosphere is important as a source of moisture and as a means for transferring energy around, and in the last part of the class we'll talk a great deal about how water helps to shape the landscape, both in the form of running water, also in the form of ice as the glaciers, and also along the coast as ocean waves. In this module we'll have an overview of the water cycle and look at where water is found on the earth and how it behaves under various circumstances. A little over 97% of all the water on Earth is in the oceans in the form of salt water. Another 2% of the water on Earth is in the form of ice, locked up in the glaciers, mostly on Greenland and Antarctica. Most of the rest of the water is underground water, followed by salt lakes, freshwater lakes, water in soil, streams and rivers, water in living things and in the atmosphere. At any given time, less than 1% of the Earth's water is involved in the hydrologic cycle, but this small amount is very critical to life. We can start the hydrologic cycle with the ocean because that's where most of the water is. Water evaporates from the ocean, then either condenses right away and rains right back down on the ocean, completing one loop of the cycle, or moves over to the land and eventually comes down as precipitation. The precipitation on land can remain as ice or snow, or it can run off over the surface and eventually end up in lakes and streams and back into the ocean again, or it can infiltrate into the ground and be stored either in the soil or deeper as groundwater. Some of the groundwater also flows into streams and eventually to the ocean again. There's also evaporation from surface waters, lakes and streams, and water in the soil, and transpiration from plants. Transpiration is evaporation from the surfaces of plant leaves, and transpiration from plants can provide a very high percentage of the moisture in the atmosphere, especially in tropical regions. The oceans cover about 3/4 of the world's surface and are connected throughout. We divide them up into various oceans for convenience, but really it's all one great world ocean. The Pacific Ocean alone covers about 1/3 of the surface of the Earth, more than all the land surfaces combined. Seawater contains dissolved minerals, which make up about 3.5% of its volume. The most common of the minerals is sodium chloride, what we call table salt, but a lot of others are also present in varying amounts. The salinity of seawater varies according to how much evaporation is going on and how much fresh water is going into that part of the ocean. Salinity is lowest where rainfall is high in the tropics and where major rivers enter the ocean, bringing fresh water in. Salinity is highest where there's a lot of evaporation, such as in the subtropics, where subsiding air means that the skies are clear, it's hot, and there's little rainfall and lots of evaporation. Salinity is also high in landlocked seas. The Mediterranean Sea, for instance, is almost landlocked, and its salinity is higher than the adjacent Atlantic Ocean. The temperature of seawater also varies from over 27 degrees Celsius in the tropics to -2 degrees Celsius in the Arctic and Antarctic oceans. That's a range of about 80 degrees Fahrenheit to about 28 degrees Fahrenheit. Notice that the temperature of seawater can get below freezing, but the water is still liquid, because the dissolved salts in the water lower the freezing point from 0 degrees Celsius to -2 degrees Celsius. In general, the western sides of oceans are warmer than the eastern sides because of the circulation of ocean currents, which follow the prevailing wind patterns. So warm water moves up from the tropics along the western sides of the oceans, then the return flow of cold water is on the eastern side of the ocean. Much of the water on Earth is locked up in the various ice caps. About 10% of the land surface of the Earth is covered by ice. Ice can be in the form of an ice cap, that is on land, in Antarctica and Greenland, or it can be ice pack, which is frozen masses of ice on the ocean, like the ice pack over the North Pole. Most of the ice on the ocean is fresh water. An iceberg is fresh water because an iceberg is a piece of a glacier that formed on land and that broke off and fell into the ocean. But sea ice is also fresh water because when the water freezes, the salts in the water are not taken up in the ice crystals. So there may be some salt water on the surface, but the ice inside is basically fresh water. Surface waters are the most conspicuous waters from our point of view, but actually all the rivers, lakes, streams, and marshes in the world contain only about 0.25% of the world's water. Although rivers and streams only hold a very small percentage of the world's water, they're important in providing the return flow of water to the ocean, and in carrying a load of sediments and dissolved materials downstream. Only about 24 great rivers of the world provide about 1/2 of the total stream volume in the world. The largest of these is the Amazon River in South America. The Amazon River alone contains almost 20% of all the water flowing in the world's rivers. It gets its water partly from rainfall in the tropical rainforest area and partly from snowmelt from the Andes Mountains. The river with the second highest discharge, the Zaire River in Central Africa, is also a tropical river, and the volume of these rivers is related to the tremendous amount of rainfall along the intertropical convergence zone. Lakes contain most of the world's surface water. Lakes are not usually formed by streams. Lakes are most common in areas where there are depressions already from other causes that just fill up with water. They're most common in glaciated areas, but lakes are also formed in sinkholes, in areas where there's limestone bedrock, and also in areas where there's some kind of volcanic or faulting activity that's created depressions. Most lakes have several streams running into them, and if a lake has a stream that drains it, that is, carries water out of it towards the ocean, it will be a freshwater lake. If a lake is in an interior basin on land, with no stream that carries water out of it towards the ocean, salts will accumulate and the lake will become a salt lake. This is called a lake of internal drainage, or of interior drainage. Most of the liquid fresh water on Earth is underground. There's more water underground than there is in freshwater lakes and streams, about 2.5 times as much, and it's distributed all over the world. Almost all the underground water comes originally from the surface as rainfall and seeps down. When water infiltrates into the ground, some of it's held in the soil, in small pores within the particles of the soil. This is water that will be available to plants. If the rock material is porous and permeable, though, the water will be able to move deeper into the soil and the underlying rock. Porous means that there are small pore spaces that can hold the water, and permeability refers to the ability of the soil and rock to let water flow through it. Permeability is related to the amount of pore space in the soil and also to how well the pores are connected. Underground water is stored in and moves through permeable rocks called aquifers. The definition for aquifer is a very practical one. An aquifer is a zone of permeable rock that contains water and is permeable enough to allow the water to flow into a well readily. So if you're digging a well, you try to find a good aquifer, because not only will it have water in it, but the water will flow through it fairly readily. When it rains, some of the water will run off into surface streams and lakes, but some of the water will infiltrate into the ground and move downwards, pulled by gravity, through the rock and soil, as long as there are any openings that it can flow through. Water moves down until it comes to a layer of impermeable rock, and then it starts to accumulate above that layer of impermeable rock. One of the terms that we use for a layer of impermeable rock like that is an aquiclude. So if you look at a cross-section of the underground area, you'll find several zones pertaining to the groundwater. The zone of aeration is the top zone. It's a mixture of soil, water, and air. After a rain, the zone of aeration might be saturated for a short time, but the water drains away rapidly. In a poorly drained area or marshy with a high water table, the zone of aeration is very narrow or almost non-existent, but usually there is a zone of aeration. Right below the zone of aeration is the zone of saturation, the groundwater zone. Here, all the pore spaces in the soil and all the fractures in the rocks are saturated with water. The bottom of the saturated zone is a layer of impermeable rock. This is the groundwater zone, and the top of the saturated zone is called the water table. The water table more or less follows the shape of the ground surface, but it comes closer to the ground surface in valleys and a little bit farther away under hills. If the water table comes completely up to the surface and intersects it, then you have a lake or a stream. The water table is usually higher in humid areas and lower in dry areas. Some deserts have no saturated zone at all. Sometimes you can have a perched water table, where there's an impermeable layer of rock up on a hill. The water percolates down when it rains, and then gets stopped by this layer, also called an aquiclude. At this point you might have a spring. If you dig a well in the zone of aeration, it's going to be a dry well. You have to dig the well all the way down to the water table in order for water to seep out of the surrounding soil and fill up the well. The level of the water in the well when the well is originally dug is the same as the level of the water in the water table. These are a few terms you should remember. Here's another depiction of the groundwater zone. We could see the main water table, and where it intersects the surface you have a stream, and water from the groundwater is seeping into the stream, keeping it going. There's a perched water table. The term aquitard means about the same thing as aquiclude, so that's a layer of impermeable rock with a small water table up above it. And where the layer of impermeable rock reaches the sloped surface, some of the water is seeping out to form a spring. There are two wells here. The unsuccessful one isn't deep enough to hit the main water table, so it's a dry well. If they dug it a little bit deeper to hit the main water table, it would be a successful well. The other well is successful because they happen to hit a perched water table, although the supply of water here isn't as great as it would be if they dug the other well just a little bit deeper. This is a view into a well. This particular well was giving us some problems because, as you can see, there were some tree roots getting into it. In fact, there were quite a few tree roots farther down, and that was using up a lot of the water and also obstructing the well. You can see the water table here is fairly shallow, only a few feet down, and the water table is even with the surface of the well. Groundwater moves into streams and often keeps them going. If you have a perennial stream in a place where it doesn't rain every single day, probably the stream is being fed by groundwater. If you pump water out of a well too fast, you can take the water out faster than the ability of the water to flow into the well from the aquifer. That means that the level of the water in the well goes down, and it goes down in more or less of a cone shape. So a cone of depression is the lowering of the water table right around an active well. It indicates that you're pumping the water out faster than the aquifer can replenish the well. If you have a lot of wells and a lot of pumping, the entire water table can go down. And shallow wells can then be left high and dry as the water table moves down beneath them. Sometimes there's another hydrologic zone below a layer of impermeable rock. This is called the zone of confined water, where there are aquifers in between layers of impermeable rock. Since the water can't get through the impermeable layer very readily, it must have come from somewhere else. Usually the aquifer is in a sloping layer that reaches to the surface somewhere at higher elevations. Then it slowly works its way down along the aquifer and builds up a lot of pressure. If a well is drilled down through the upper impermeable layer to the aquifer, this pressure will force the water out to the surface. This free flow of water is called an artesian well. This is an artesian well in Australia. Artesian wells can even be found in arid areas because the water may have come from a long way away, and it can be a very important source of water in arid places. The thing about groundwater is that a lot of it has been accumulating where it is for hundreds or thousands of years. Once people find the groundwater and start pumping it out, it may be getting pumped out at a much faster rate than it's being put back in. In parts of the southwestern United States, in arid regions, the recharge of groundwater goes on at an average rate of less than an inch a year, while we might be pumping out the groundwater at a rate of 20 or 30 inches per year. This means that what we're doing is mining the groundwater. That is, we're using it up. We're not using it as a renewable resource, and eventually it will start running out. In the meantime, we need to figure out better ways to conserve the water that we have and to recharge groundwater supplies.